Okay, so we are now in the agent model. So the agent model is the model that runs directly on the agents, the robots. Um, so first thing I'm going to highlight once again, because very important. It'll save you a lot of headache if you don't do like me and forget about it. Always in the third instance, make sure that you're in utilities. And the reason for this is that when you either monitor and tune or build, deploy, build, you don't use this, but when you build, it creates a file. The file is here. It is the mammo agent, and this is the one that is being executed on the robots. First off, I guess that is something I should specify. The difference between monitor and tune and build. So when you do build, it simply builds the model. So it creates this file, but it doesn't send it on any of the robots. When it is more optimized when you do it like this, because it's not made to be observed. So there's I'm pretty sure it will just ignore, for example, all the displays, stuff like that, which is not necessary for when it's simply built. Monitor and tune is going to run directly on the robot. So for it to work, the driver always needs to be started. So the order of things is at the base is the driver. This controls directly the wheels, the motors, and the stuff like that. And on top of that is the agent, which communicates with the drivers. And then there is the control center, which communicates with the agents and with the union. And the union that communicates with the control center, which communicates to the agents. So that's the hierarchy with this. So you don't need to worry about the drivers. It was made by Quanzer. I modified it a little bit to suit our needs, but you don't need to. You really don't need to worry about that. Unless you want to, yeah, unless you want to. In which case, the model is here, custom driver physical. I mean, you can open it up and look at it. If you have any questions, I'll be happy to explain to you what's going on. So yeah, but we won't get into that today. So hardware settings here. This is important. Code generation interface. Over here, you see QBP3. So what is going to happen when I press monitor and tune and robot 3 is online? This is going to push this file here. Is going to first build the file if it's been updated, and then it's going to push it on robot number 3. If you do monitor and tune and robot number 3 is not online, it's going to get stuck for a few minutes, and then it's going to say that well, it doesn't work. So yeah, just make sure that the robot is online and it's the robot that you want to speak to, or actually observe. So if you make changes to this, you will need to, well, of course, rebuild it. And when you rebuild it, you stop here all the agents. So just double click here. So 1, 2, 3, 4. Now I'm not gonna do it because the robots are offline, but you just do that and it's going to stop the agents, and then you can start them again. Or actually you can just do it here. I had forgotten I wrote that last week to make it easier. So you just do 1, 2, 3, 4. It's going to stop the agents, and then it's going to restart with the new model. So yeah. Okay. So don't make the mistake of forgetting to restart the model on the other robots and simply doing monitor and tune, because then the other robots are going to be running an obsolete model, and the robot you're observing is going to be running the new model, which is going to create an incoherency that you are probably going to wonder why the hell things are behaving the way they are. So just make sure that all the robots are always running the same by following that simple step of building, and once it's done building, restarting the agents. Okay, so here again we have storage, which is just the variables used in the system. It's pretty much global variables, if you will. Stop forward here. So when the robots, there's different reasons why they would want to stop forward. For example, it wants to avoid a collision, so it detects that if there's another robot, it's going to not be allowed to move forward anymore, and but it is still going to be allowed to turn. Another case is the success here. So when the robots successfully reach the theoretical target here, so when it reaches that zone, then it stops, and at that point you'll also notice that the light turns white. This is just to indicate that it succeeded. I think there might be other situations where it does that, but yeah, stop forward, stops forward, but doesn't stop turning. And there's a stop, so we can ask the robots to stop locally. Yeah, that's pretty much it. These here, the parameters, now these, as you can see, are read from the data stores here. So actually, of course, you don't change them here, you change them in the control center because you're controlling every robot at once. So this is just to visualize which ones are active for convenience. We've seen all that in the other one. Anything else? No. Sure, we've seen everything. Okay. This just says which bot you're connected to. So when we connected to bot 3, this will reflect that. It doesn't get it from there. It actually goes on the hard drive of the robot to see what its ID is. And if your algorithm is activated, it's going to say it here too. Okay, so this just validates that the union model is correctly running, and that the control panel is correctly connected, and if all that, and that it doesn't have an order to stop. And if all that is valid, then it will activate here. So where should we start? I guess we will start here. So we can start with the data bus here. Okay, so this is the little script that simply looks for the ID of the robot on the file. Once it does that, it will stream out the bot, but it will also, all the ports that are going to be open are going to be open with that number. So as you can see, 1721 and then the bot ID. So that avoids that we make 6 models for 6 different robots. And so yeah, so this receives the union data. And the first one received the union data. Second one here receives the commands. So this one was the one on the left in the other model, and this one is the one on the right in the other model. And all of this is moved here, and again, color-coded green. So you can, if you want to add some instructions, this is where you're going to do it in the green boxes. Generally, so I'm aware that my color choices are absolutely hideous, but they are meant to be practical and not beautiful, which they definitely are not. Sorry about that. If they're too much of an eyesore, I invite you to choose a nicer palette. Okay, so ID broadcasting. This simply broadcasts 11111 or 22222, depending on which one is online. Yeah, that's pretty much what it does. So yeah, this is just so it doesn't overload overload communication. We don't send it continuously. We give a period. This is for the synchronization. Okay, and I think we are done with this. So just to recap, the union matrix, all the instructions. That's what we have here. So the union bus here, and the data bus here. Could have used the go-to here. Actually, would have been a little bit cleaner. Yeah, so that's what we have here. So once this is activated, this subsystem is activated, this subsystem, this one, they're all activated. It goes through your algorithm, even if just that. Okay, so okay, so here OTH comes. So this says the information it's receiving from the other robots. It's here. You're only going to see this if there's open communication with other robots. So we are not going to go in depth into your algorithm just yet, because I want to reserve a video just for that. So actually, when your algorithm is not activated, it just flows right through this subsystem and goes straight to the mapping. So the mapping here, so this basically plans and maps. Yeah, so this here, it finds a clear target if the target happens to be in an obstacle, and it will either move it on the closest point on the perimeter of the restricted obstacle, or on the closest point on the perimeter of the obstacle near the agent. And there's a little bit of gymnastics here with yeah, for we flip the XYs a little bit all over the place. That's because of how I initially coded the other functions. Kind of messed up there, and I was lazy, and well, came back and haunted me later. But yeah, everything works. So we find the clear target first, and then we get the next waypoint. So Yeah, so this just uses the union contour to create a map and calculate the path from the robot to the target, taking into account the obstacles. So it finds the fastest path, taking that into account. Okay, and then number of points. Let's see that later. Okay. So the navigation here. This. Yeah, basically this just takes the next waypoint, adjusts the angles, moves the robot in that direction. Also stops when it reaches the target and stops turning when it reaches the angle. Yeah, I think that's pretty much it. Yeah, of course, the setting is a little bit different when your algorithm is activated. But yeah, nothing too complex here. It's just take that off. Okay, so yeah, yeah, it always uses the tolerance to determine that. So the fuzzy, as I said, was not implemented because of the issues we had discussed. So where it would need to be retuned. So it's not implemented. However, it could be implemented. Okay, I'm sorry about that. So yes, so actually it's ready to be implemented. All the building blocks are there. You would just need to activate it. Right now it's not activated. So so we have here the fuzzy controller. Now what you would need to do if you wanted to work is go into the code here in utilities. I believe it is actually, this is what you need to regenerate with the proper parameters. Just I think I had made separate. Yeah, okay, I'm not sure, but yeah, you just need to redo another one that's calibrated. I don't know how to calibrate that. And once that's done, if you want to have the fuzzy input and fuzzy output, you just uncomment these, and it's going to create the files that you can analyze. But to be able to use it, you're going to simply have to remove the terminator here, connect it to the top here, and then you'll be able to activate the fuzzy controller by doing Control-Alt-F. So that's all that needs to be done for this to work. So here's my basic controller. I didn't know what to call it. So this uses, as I said before, second order low pass filter to remove the noise. We'll add a little bit of stochastic movement here just to prevent deadlocks. It's very little. There's sigmoid asymmetry, and that's just to because I wanted to accelerate faster when there's no obstacles, and take more time to slow down so that it doesn't hit the others. So the steepness and the symmetry, and once again, that's all controlled in the control center. Nothing is hard-coded. Everything can be adjusted in the control center. So yeah, this is basically the controller here. I put more comments than I usually do. But yeah, so just it should be pretty clear, I think. If not, again, don't hesitate to reach out. So yeah, the cutoff frequency, the damping ratio, all that is inherent to the second order low pass filter. As you can see here, I put the option of adding stochastic movement, but it's at 0. So in the for the angle, there is no stochastic movement. It's just there as an option, keeping it open. Speed limit control, making sure it doesn't go over the Vmax, Vmin. Safety, so it stops moving forward, or when it stops, all of that is here. So this is basically the yeah. So here, when your fuzzy system is activated, it will still, after that, need to go through the speed limit and safety trigger response. So that's why the change is here. So yes. All right. So this just executes that when it's activated. So if this is not activated, this just sends zeros. And QBP hardware here, this is what communicates with the driver, so the driver model communicates with the motors and the cameras and all of that. So this sends the information downward to that. So that's where it tells it, what speed to go, and what speed, what angle, all of that. So yeah, that's pretty much it for that. Yeah, this is where the communication between the agents happen. So as it's written here, the information is broadcasted and picked up by the control center and any other agent that is listening on the active agent's port. And the agents only listen on the ports if the agency vector tells them that they're allowed to communicate with the other agent. So I could have simply opened up the communication, everybody communicates, and we select which ones we want to communicate with the agency matrix, but that adds overhead. So the idea was to reduce overhead, which is why we're not making them all communicate in the first place. At least I assume that's the reason. So just to make it as realistic to the intent as possible, they only communicate with the robots that they are allowed to communicate with. So you have the outbound communication here. So this broadcasts to everyone different information. So the W matrix. So now we're actually getting into your algorithm. I will stop the video now because it's getting long, and I will speak of all this in the next video when we speak of your algorithm and how it was implemented.